What did you guys say? What is Faraday's law? Do you want to start us? Go ahead.
Electromotive force in a solenoid is directly proportional to the number of loops and magnetic flux, and inversely proportional to time.
Okay, so that would be a very literal interpretation of what that says. And I mean this. I don't mean this in a bad way, but if you say that, it appears to me that you don't really understand what it means, and that's okay because I threw this at you at the very end of the class last time, right?
Yeah.
So we really haven't, pulled this thing apart yet. Other descriptions, other explanations of what is going on there? Matt, what did you say?
Probably wrong. But
That's okay.
The number of loops increase as the number of loops increases, the flux decreases.
If you're going to have a constant what?
Yeah.
Yeah, so if you're going to have a constant EMF, what is EMF also? What's another word for EMF?
Voltage.
Voltage. So I'm just going to start using voltage because EMF is just kind of annoying. So this is really just voltage, right? Okay. And so Concha, you said that if you're going to keep a constant voltage, then the number of loops goes up if the flux goes down.
Yeah.
That's true. That's true. Yeah, it's the kind of in the same vein. I would say that that's not like it's kind of making an observation about that. Yeah. Go ahead.
The number of loops as a charged particle moves through the solenoid. The number of loops each loop kind of acts on it individually almost because they're almost circles. So if you increase the number of loops, you increase the force proportionally to the number of loops acting on the charged particle.
Okay. So by increasing the number of loops, what are you changing then?
The strength of the magnetic field.
Mm-hmm. Yeah, so you're changing the strength of the magnetic. Well, what do you mean? Sorry, hold on.
Or more like you're increasing the length of the magnetic field and the force acts on the charged particle, and because it's acting on it for an amount of time proportional to the number of loops, that force adds up.
Okay.
Has a larger area to work on the particle in.
Okay. So we're kind of there. Let's take a step back and look at this kind of as a cause and effect thing. You guys know that I like to write this as A equals F over M, right? Just Newton's second law.
Yeah.
Why do I write it that way?
One thing causes another.
Yeah, because the force acting on a mass causes an acceleration, right? That's why I like to write this way. This one is already written as a cause and effect sort of thing. Okay? The effect of all of this business on the right-hand side is that we have an induced voltage. Okay? So an induced voltage is caused by what?
Changing the magnetic flux of a solenoid.
It's caused by the change in magnetic flux, yes. So induced voltage is caused by a change in flux. What in the world does that mean? What does a change in flux mean?
If the area or magnetic field strength change.
The area of the what?
The shape within the coil.
Okay. So the area of the coil or the loop. Okay. So if it gets bigger or smaller, or what was the other thing you said, Matt?
Or the strength of the magnetic field.
Yeah. If either of those changes, or if both of those change, any change in either of those causes an induced voltage. Is that okay? So another way to look at this flux thing is to think about it as magnetic field lines going through a loop. Are you with me there? So I have this picture, I think. Nope, not that one. This one. This can kind of give you a sense of what flux is. So these red lines are magnetic field lines. Is that okay?
Mhm.
So you've got like a north pole and a south pole of a magnet, for example. Okay? Hi, what's up? Thank y'all. Does it take two of you guys to walk up here? So what's going on? Okay. Thanks. Red lines are magnetic field lines. This thing is a coil that's sitting on end. So if I take a coil, oh, I don't know, like the ones that we used yesterday. There we go. So this coil like this, right? You guys with me there? I'm turning it like this, and that's what's going on here. So the magnetic field lines are going through the coil, okay? That is the flux. So you can literally think about flux as the field lines going through the coil. If I make this coil smaller, so I get a different one, these are all like tied together here. If I get this one, so if I have the same magnetic field, like it's traveling in this direction, and I hold these both up, which one's going to have a bigger flux? This one, right? Because it's got a bigger area. Okay? I can turn up or turn down the B field on either one, and that would affect the flux. Okay? The other thing that I can do to affect the flux is to turn the coil, because that changes the effective area, or the area that the magnetic field is going through. Okay? So if instead, so let's imagine that the B field is going this way. So coming like from back there up here. If I have it like this, I've got flux, right? I can measure that flux by measuring the area and measuring the strength of the B field. If I turn it like this, is there any magnetic field that's actually going through the area now? There is not. There is no area going through, or no magnetic field going through the area, because the magnetic field is going this way, and the area is open up and down. So the magnetic flux now is 0. Okay? Here it's maximum. Here it's 0. Somewhere in the middle, it's somewhere in the middle. Does that make sense? That's why it's a dot product. That's why it's a dot product, because it depends on the angle between the face of the area and the B field vectors. Is that okay?
Mm-hmm.
Does that help to make more sense of what flux is for you guys?
A little.
Tell me some more. Ask me some questions. I think that'll help me to explain things to you better.
Like, is it quantified by the area of the coil?
It's quantified by both the area and the magnetic field. So it's a combination of the two.
Okay.
So
And the only area we care about is the open, like the area.
the area that, oh sorry, you speak. Go ahead.
The open area. How big the loops are within the coil.
Yes, but if my magnetic field is going this way, it's not like I've changed my loop.
Well, no, that's essentially 0, but still, you're only considering the area of that open area part.
Yes. Yes. So it's this part that's got B field going through it. Is that making sense? Like if I, oh man, I could have made a big disaster there. If you look at like the shadow of this thing, sorry, as well. Where's my shadow? There it is. Can you see that? Can you see that? If I turn it, the area is smaller, right? Because it looks like there's only, so like if you use the light, pretend like the light is your magnetic field, right? Now I've got a maximum. Now it's getting smaller, 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 0. Bigger, 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 bigger lots. Smaller, 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 0. Bigger, 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 bigger lots. Does that make sense? So it's the area, but it's also the area that has B field going through it. How are you
So
feeling
if
about
We're
that?
at like the 60 degrees. We
Mhm.
would have to refine the area
It wasn't fair.
based on, it's not a circle anymore.
So you don't have to like directly find, but you would just do the area times the cosine of 60, and that would tell you how much is being impacted.
So the area is always constant unless you actually like change the coil.
Right, unless I change the shape of it.
Yeah, yeah.
Yeah, yeah. Zach, did you have an insight you wanted to share?
Now we're good.
Are you sure? Can you tell us what you were talking about? Just because
Talking
I'm.
about if the motor one was based off Faraday's law, but
It is.
it is. I thought it was mostly the charge, like the current going through the wire, so that would feel the pull.
Let's talk about that in just a second. Hold on to that for just. Is that okay?
Yeah.
Hold, because that's where I'm going to go. I just want to make sure that this part is okay. So, a change in flux. So flux. Let's back up here and say flux is this phi thing, which is a times b, or a times b times the cosine of theta. And this angle. I want you to write this down because I think we didn't quite get through this last time to really make it make sense. Okay. This angle is the angle between the area and the magnetic field. So that open area and the magnetic field. So again, if we're going to put this equation into words, not just literally writing one thing into another, but actually sounding thoughtful about what this says. The induced voltage is caused by a change in flux. So if you have flux, does that mean that you have a voltage?
No.
No,
No, you have to have a what?
no loops.
Your number of loops could be 1.
You have to have a change in.
But the key that's going to give you a voltage is the change in, right? We can go back to looking, and I do want to do this, so I want to make sure it makes sense to you. If we think about the motional EMF thing that we talked about last time, if you just have this bar sitting here, will the light bulb be lit up?
No.
No. What is it that I have to do to that bar to make this light bulb light up? I have to move it. In moving it, what am I doing? Changing the area. And by changing the area, I'm changing the flux.
Do you have to move it right continuously, or can you move it left hand?
What do you guys think?
I think you can move it either way.
The force naturally moving it left. Or isn't there a force?
Once you started moving, there's a force moving it left.
Okay. Speak louder, Matt, and talk through what you're saying, because I think it's important.
Wasn't there an initial, like the magnetic force
Mm-hmm.
was to the left already because your B field, wrong here. Your B field is going in and then, let's see. Okay. So your velocity is going to the right.
Okay, let's revisit this. This is important, big stuff. So there are 2 right-hand rules that we have to use for this one. There are 2 processes. The first one is to figure out how the separation of charges is going to happen. And in that one, you're going to use your velocity, your finger for velocity going to the right. Does that make sense? So your velocity goes to the right, B field goes in, positive charged particles are going to feel a force where? Up. So that gives you a bunch of positive up here and a bunch of negative down here. Right? Mm-hmm. We put it in this circuit, and now not only are those charged particles feeling a force that way, they're also going in a loop, right? So now you've got a motion of positively charged particles in this direction. B field goes in. So this bar feels a force where?
To the left.
Left.
To the left. Does that make sense? That's what you were talking about, I
Yeah.
think, right?
Yeah.
That there was a force going like this, FB. But Lena wanted to know, say your question again now.
Do we have to move it to the right, or can we move it left and right, because that's still a change in the area?
What do you guys think?
I think either one works.
We were just
Like,
But then
wait,
we
I
do
would seem
it
like
left
oscillating
and
the more it's like moving back and
it's gonna
forth.
change,
Yeah,
right?
sure.
Mm-hmm.
But it's still gonna work.
Yeah, we were just
Yeah,
moving.
it's just that, so go ahead, speak.
We were just moving it right, that way if they were like equal, then we could keep, what was it, something the same.
We get the voltage.
Yeah.
Yeah. So to start out, we just moved it one way, right? And if we just move it to the right, then the current is always going to go like this, right? Okay? But if we move it the other way, so we have our velocity vector going to the left, now our force is going to go to the right. Which way is our current going to go?
Clockwise.
Clockwise? Okay? And so then, if you start moving this thing back and forth and back and forth and back and forth, what are you going to get that makes this light bulb light up?
Alternating current.
Alternating current. Just go back and forth and back and forth and back and forth. Yeah, that's how our light bulbs light up, right? Yeah. That's exactly it. Does that answer your question? Okay. So as long as the area is changing, we know the flux is changing, and as long as the flux is changing, we have a potential difference. And as long as we have a potential difference, we can light up the light bulb.
Which that's how the motor thing was Faraday's
Boom.
law.
So let's do that. Let's talk about that. So the motor thing. Should kick Jonathan out for this, but I won't because I want to hear it too. Whoa, that got little.
I heard once about a left-hand rule for motors, but I doubt that's this.
Don't say left-hand rule. That's not right. Jeez. So talk to me about the motor. So here's your cup and your battery and your magnet and your little coil of wire. Talk to me. Tell me the story. I haven't read your letters yet.
Okay.
Start us off,
Don't
Miles.
read our letter because it's going to be wrong. But how it actually works is not how we originally supposed, which was...
Well, it's like a combination of them.
Yeah, so the combination, one way it's working is, hey, you have these electrons that are moving and a B field, so right-hand rule...
Okay, slow down. I'm not following you.
Can I go to the...
Yes,
Yes.
please.
Okay. So there are kind of two-ish things at play here which make it go spin. First off, let's suppose that this here's the positive end, that here's the negative end, so...
This is the positive and this is the negative?
Yeah.
Okay.
So current goes here and then... Woo!
Okay.
So it's going to the right, up on the top, and then left, down at the bottom.
Okay.
So let's also suppose that, why not, that the B field is going upwards.
So this is the North Pole and this is the South Pole?
Yes.
Okay.
So then right-hand rule says that velocity that way, B field that way, force that way. It's going to spin. Top half is going to spin out of the page. And then when it's going the other way down here, the electrons or current is going to the right down there. That end will be pushed into the page, so then woo, spinning. That's one way. Other way, Faraday's law.
Well, yeah.
Do you want to speak?
Not one. I mean, that's part. of it.
That's part of it. That's part of it. There's two ways it's going at the same time. That's what I'm saying. It's part of it. Other part, the Faraday's law part, is that you have your EMF. I'm just matching the equation in my head. EMF, that's constant. Your voltage is constant because of the battery. The number of coils you have is also constant. So you have to have then your magnetic flux, which comes from the change of, your magnet is just the same, so it's just changing the area. That's how your magnetic flux is changing. So it changes by the area because as the motor spins, that open loop of area is going to change, like Ms. Conley showed with the light and this loop. That'll be changing, which causes a change in magnetic flux, which completes the equation, yay. So the area has to be changing the whole time, or else it does not work.
But if that's just affecting the voltage and inducing a voltage.
Well, the voltage is constant because of your battery.
Okay. Yeah. So
If
then
we rewrite it to
how does
solve-
the change in
Yeah,
magnetic
you're
flux-
basically rewriting the equation to solve for the flux.
Wait a second.
So basically,
Talk.
So,
Because you're mad at me, but my answer is sound, but not there yet. Go ahead.
well, I was saying Faraday's law is based on finding the induced voltage, but you already have the constant voltage in the battery. Faraday's law has nothing about like force or something to keep it spinning. That's what I was thinking. It was just that. I mean, yeah, Faraday's law is working, but it's not
It's not doing it
doing it. Is it doing anything to make it spin?
a little bit.
Just because the induced voltage is also like.
A little bit. Hold on for just a second to that. It's more subtle than that. There's actually a lot of good physics in there, but I want to make sure that this part is making sense first.
Wait, so if the change in magnetic flux is constant, does that mean that the motor isn't spinning uniformly?
Say that one more time.
If the change in magnetic flux is constant, does that mean that the motor isn't spinning uniformly?
What did you say?
Because it's a circle,
Uh-huh.
so I just don't think it would,
It's not linear.
Yeah. as it spins, it's not, if it spins constantly, the change isn't linear.
Yes, I would agree. There's a whole lot of momentum that's keeping it going, the way that I look at it. Yeah. Akanksha, you looked like you wanted to say something, or maybe I was just dreaming. Was I just dreaming?
With the, oh, sorry.
No, go ahead.
With
No.
the Faraday's law, doesn't that induce alternating current if it's spinning? Since it's spinning, it's switching, right?
Right.
So switching. So wouldn't Faraday's law be then actually helping work against the spin? Okay.
It does much of the time. Yes. So there's one piece of Faraday's law that fits in this, but not, and some of it is applicable and some of it is not.
Electromagnetics.
Just because you wrote a letter that didn't include the words Faraday's law, that doesn't mean it's wrong. I want to make that clear. I haven't read your letters yet. The first part of it, the part that's really, really important, you could have explained a long, long time ago, just with the idea that Ørsted came up with, that Miles was explaining earlier. If you've got a current, I'm going to say what you said, but in different words. Is that okay? If you have a current running through a wire, if I take this magnet off of here, is this loop going to spin? No. What's going to happen? If I take the magnet off of here, what's going to happen in the story?
This is going to be a circuit.
It's just going to be a circuit, right? That loop's going to get warm. Do you agree?
It did get one.
It did. Good. Should have. Had a lot of current running through it. Why does the magnet matter?
Creates a magnetic field that we move with the charges in the circuit will be attracted to our motion by the. I don't even. Is that a law? Is it called or just?
It's just the.
Force of magnet.
I'm sure there's a name for it. I don't know what it is. But, well, yes, there is. The Biot-Savart law.
Biot-Savart law.
Right? The Biot-Savart law says, what does it say? Do you remember?
Moving charge in a magnetic field will field force. Is that what?
No.
That's not
It's even simpler than that. A moving charge is going to create a what?
magnetic field.
Magnetic field.
Okay.
Is that okay? Moving charge is going to create a magnetic field. So you got this current that's moving charges. Get this right hand out. Right? This right hand rule out. Okay? So you got your current going this way. B field's going to be created through that loop. It's going to create a north pole on one side and a south pole on the other side, depending on how you have your magnet set up. Some of those little loops you had to give it a little kick, right? Because if it was set up so that you had, if this was your north pole, then the one on the bottom was south, then they're just going to be attractive and they're just going to hang out there. If you tip it a little bit, then
It's not quite in
it's
equilibrium
going to start
anymore.
spinning. Because then your north pole is going to be repelled from your south, or your north pole is going to be repelled from your north pole. South pole is going to be attracted, and it's just going to keep going. It's not going to get to a spot and then stop because it's already moving. Okay. So really, it's the Biot-Savart law that makes this work. The other part of it that has to do with Faraday's law has to do with the negative sign. We're going to jump in there in a minute, but not yet, because I want to do a problem with.
I wanted to talk about current.
That was kind of what happened there.
That was a low key. I'm salty.
Why? Because
About their letter.
it's okay. You wanted to talk about the current going through the loop.
Because current induces a magnetic field.
That's true. There are lots of good ways to explain it, though. Because Miles didn't say that when he explained it, and he did a good job, too. There are lots of good ways to explain it. What Zach was saying earlier was that if you have this thing happening, okay, that motion happening, then you have a change in flux, which actually creates a voltage, right? It creates this thing called back EMF, actually. That actually works against the spinning that's happening, trying to get it to go the other way. It creates a voltage that's opposite of the voltage that the battery creates. It's weird. So Faraday's law actually works against that. Again, not something that you whatever should have used. I just wanted to throw that in there. Okay. Before we move on and talk about negative signs, they're important. I wanted to do a problem with this, but I want to make sure that this is making sense to you first. Are you feeling okay with the idea of flux now? B field going through a loop. The B field gets bigger. The loop gets bigger. Either one gets smaller. The angle gets smaller. Any of those things induce a voltage, which also induces a current. Okay. Let's try this problem. Let me give you the setup for this problem first, and then I'll let you work on it. A square coil. Our square coil is very efficient. I mean, it seems like it'd be hard to make, but it's easy to do calculations with. That's why we chose it. Okay. And they work the same as any other shape. You can have a blob, like I don't know what happened to this coil. It's not very circular, but it would, still it's a coil. Anything that's a closed loop will give you something interesting with Faraday's law. Size of 5 centimeters contains 100 loops that is positioned, perpendicular to a uniform 0.6 Tesla magnetic field. It is quickly and uniformly pulled from the field. So the way we can imagine this, if my table is emanating magnetic field upwards, and I have my square coil, pretend this is a square, it's like this, I'm going to pull it like this to a place that doesn't have any magnetic field. Magnetic field, no magnetic field. Got it? Okay? To a region where V drops abruptly to 0. There it went. It takes 0.1 seconds for the whole coil to reach the field-free region. Part A says to find the change in flux, and then some other stuff. Can I let you play with that for a little bit? Or do you need more pushes from me? I believe in you. Get started there. And then if you need pushes, you let me know.
Is this on the book?
Wait.
Or is this...
It's a good question. I'll look and see. I can't remember for sure.
So it's perpendicular to the field.
So let me turn this on so that So I'm going to just say this one more time. That area vector, it's the same as it was for Gauss's law. It's been a while. We're going to come back to Gauss's law and learn it again because I think we need to. The area vector for an area, when you're talking about flux, is perpendicular to the area itself. So this is the area vector. The B field is going parallel to that. There's the B field. So the angle between those two is 0. And since it's 0, the cosine is 1. Is that okay? Yes, no, talk to me. Yes, Ms. Cobbling, that's great. Sweet. All right. Part B, find the EMF and the current. Well, you can find the EMF. That's the voltage, right?
Yep.
And what'd you get for that?
1.155 volts.
Negative 1.
How many?
Negative 1.5.
1.5 positive volts.
Why did you get 1.5 positive and not negative?
No, 'cause it said negative, and then I said the change was negative
Because
And if the change is negative,
times negative.
and Faraday's law has a negative sign in it as well,
Right.
negative times
negative n, right? Yeah. Negative times negative gives you a positive, yay! And then current, how did you find the current?
E equals IR.
I did that.
That one's easy. Yep. And what'd you get?
0.015.
1.5 times 10 to the negative 7.
How are we doing on or on A and B?
Mhm.
You okay there? Okay. Part C, how much energy is dissipated? So, what does that mean? What in the world does that mean? If instead of just having a coil, you had a coil that had a light bulb hooked up to it, let's say. Is that possible? Can you do that?
Sure.
Sure, why not? Wire a light bulb up. And I take this right here, and I pull it over here. What's going to happen to that light bulb? It's going to, what'd you say?
It's gonna go out.
Was it on over here? Let's imagine this. Is the light bulb going to be on if I just hold the coil in the magnetic field here?
No.
No. What about when I move it around over here?
No.
No, why not?
You're not. The flux isn't changing.
No flux change, right? I'm moving it, but it's all same flux, same flux. What about right now?
Yes.
What happens then?
Yeah, you should change the magnetic flux.
I'm changing the flux, which means that I've got a
Voltage.
voltage, which means that I've got a,
Current.
which means that my light bulb will be
Um,
on. And then what about when it gets over here?
no.
It'll now.
No.
No. Why no? Why?
No change in flux.
No change in flux, no light bulb on, right? But there's that brief moment when we have that change in flux, that brief moment, that light bulb will be on. If you think about the light bulb turning on, does it make sense that that light bulb is changing that kinetic energy then into light energy? You with me there? Okay? That light is dissipating power. That's what we're talking about. Energy has to be conserved, so all that has to come from something else. This is just the way, this is an easy way to relate something with a circuit to energy dissipation. Is that okay? So P equals V squared over R. E is equal to P times T. We know that it takes 0.1 seconds for the whole thing to happen. So you can figure out how much energy is dissipated. How much energy did you get? Is it a lot?
2.25 times 10 to the negative third.
What are the units for
I
that?
only got negative second.
Yeah, it's only negatives.
We have dissension. Figure it out.
Because it's 2.25.
Yeah. What is 1.5 squared, Miles?
1.5. Wait, is that R is resistance, right?
It is.
Yeah.
So 1.5 squared divided by 100, 0.25 divided by your 10. That is multiplication. Wait, that's P, so P times 0.1. Hey presto, 0.0225.
And it's only a 10 to negative 2.
It's in the negative third, maybe.
No, it's not. Still a negative 2. Move it decimal place. So cut out.
Move this one place only
Okay,
twice
somebody
together,
come up and do
0.2.
this. This is ridiculous. I don't know why you're fighting.
Unless I messed up somewhere.
0.0225.
Oh my god.
I'm glad that we all agree now. 10 to the negative third, don't forget time. Units on this are what? Joules, because we're not going to forget what that is measured in. All right. Then we got the average force required. How much force does it require? Well, I don't know. How do you do that? Relate it to what we know. Usually if you have a part D, it's related to part C. Not always, but often. How do you want to do that? Matt, go ahead.
Should we use F equal to B?
F is equal to, what'd you say?
B, I,
For
L.
L.
L, you would use the
Would you? I don't know.
Let's try.
Let's think about it before we just randomly plug things in. I know, that's kind of crazy. What is this equation talking about? Let's figure that out. This is the force.
Well, let's say if there's a current going through the wire in a magnetic field. Oh, but it's the magnetic field's changing.
That's supposed to be an I. I don't know what happened there. This is the current, or this is the force that would act on a current carrying wire that has a length L in a magnetic field. But what?
Well, there's also a square, and it was going around. So that force that you're finding there, I think, is 0 since it's the loop. Because they'd all be pointing in, wouldn't they?
Well, let's figure this out. I kind of like this. Okay, so I'm going to put my B field like this. And I'm going to put my loop like this. And Thomas, you're going to decide which direction that current's going. I don't care, you pick. Clockwise, counterclockwise.
Counterclockwise.
Counterclockwise. He's wild and crazy. That means the current is going up here. Current is going down here. And like so. And like so. Okay. So let's talk about this. Is there a force acting on this loop? Figure it out.
Well, the theta, again, is between...
Four forces in the loop, they're just all equal opposite. So,
Yeah.
Get your right hands out, friends. I'm not going to tell you the answer to this question. I'm going to tell you that magnetism can be tricky because there are lots of little pieces to it. And if you're not actually applying and thinking about it, it's not going to work. Talk to me.
Cancel the grip.
You can talk to. What are you figuring out?
I think all the forces directed outwards.
Yeah, no, all the forces are inwards.
Oh,
Yeah, they're
Right,
all-
'cause that's
they're
all
all
going
to
into the
center-
page.
center of the-
Which is what we had found before.
voltage and size, right? Oh wait, no, in the page.
Which would
In
mean-
the page. One, yeah.
yeah, they would all cancel out.
Okay, so is that... Let me ask another question. So you're saying the net force on the loop there is 0? Yes, no?
See.
Okay. Is there going to be some force required to pull that loop out of the magnetic field?
Yes.
Yes.
What evidence do you have for that?
Because if it didn't take any force, because you have to, well, because you're converting the pulling it out into electrical energy in the loop. So I would assume that there'd be some sort of work from here pulling it out.
Did you guys catch that?
Yes.
Okay,
Would it
because
be a
otherwise-
would it be one-to-one?
What do you mean?
Like the work that it would take would be the same as the work put in. So okay, so
Yeah, because energy has to be conserved,
So
right?
then you would just divide the energy thing by 5 centimeters. Because I guess you're pulling it 5 centimeters out.
What do you guys think? Does that make sense?
Mm-hmm. Makes sense.
Yeah? Okay, do it.
Is that right?
Yeah.
So,
All of this stuff fits together.
0.74.
We don't do any of this in isolation. It all fits together. We'll come back to this because this is going to be interesting again soon, but not yet.
Oh, we do use that.
Would I use this equation? Not for this part of the problem, no.
Equals force times distance.
What equation do you use?
Work equals force times distance.
Mm-hmm.
So force equals work divided by distance.
Mm-hmm.
Okay. The thing that I was thinking about was like inside the loop, where like if you're moving it, but that would take no force because it's not actually inducing any. Like if it's in the magnetic field but it's not coming out yet.
Correct.
That would take any.
There's no force, yes. Yes. That's true.
So your delta E is just what you kind of see.
Yeah.
Work is changing how it's.
Yeah, that's the only energy that's dissipated. Because it's moving at constant speed. So the kinetic energy is still kinetic.
I swear, I just want to.
Bless you. How are we doing? How much force is it? Is it a lot? The distance is 5 centimeters. Yep. .5 what? Times 10 to the
-2.
Is that okay? Miles, you look like you are on the verge of having a question, or maybe I'm wrong. Am I wrong or right?
I mean, it's a question I can answer taking a glance at the equation sheet.
What's the question?
Work is power times time divided.
Work and energy are the same thing.
Oh.
Right? That's the work energy theorem. Work is equal to change in energy. Is that okay?
Yeah.
Sweet. All right. All right, can we move on?
86.
Here we go. Ready? A whole law for a little line. Are you ready for this? You ready? Excited? Nobody's asked me yet. I think it's interesting. Maybe it's just because you don't even know to ask. Why that's negative. Anybody want to ask?
Why is that? Ms. Carplin, why is there a negative sign in Faraday's law?
That's a really good question. I'm so glad you asked. Let me tell you. There was a guy named Lenz that explained it. He has a whole law. This is a whole law
To explain what
for a negative sign. Okay? Most important negative sign in all of physics right here. Are you excited? Here it comes. Lenz's law. Lenz's law describes the direction of an induced current. Here we go. It's a lot of words, and we'll explain what it means, but it's important to write these words down because I think it's there. It helps to put it all together. The current caused by an induced EMF or an induced voltage travels in the direction that creates a magnetic field opposing the change in flux through the loop. Crazy, crazy stuff. The current that is caused by an induced EMF travels in a direction. So this negative sign is all about the direction. It travels in a direction that creates a B field that opposes the change in flux. The shorter version of this is if you think about a little kid, like a toddler that's playing and happy on the floor, do you mess with it?
No.
No, you don't, right? If you change its surroundings, it's going to react. Are you with me there? Okay? It wants to oppose the change. Current loops do the same thing. loops want to oppose the change in flux. Okay? We're going to get our right hands out and I'm going to explain how this works. I'm going to turn this off. Or maybe they're just really stubborn people because I think that they're toddlers. You guys think that they're teenagers. I guess it's just whoever you live with that is ornery. Right?
Cats.
There are probably adults that do this too. All right, let's try this. Take a look at this one. So here's your loop. I want you to hold on to your loops because I think they're helpful. You've got a magnet, a permanent magnet now that's moving towards that loop. Do we have a change in flux?
Yes.
Yes. I want you to tell me which way the current's going to go from this side of the loop, because if you look at it from this side, it's going to be opposite.
So on the side closest to us,
The side that the magnet is on.
Counterclockwise.
anti-clockwise.
Yep.
You guys agree? Counterclockwise? Why?
Because it wants to induce a flux opposite of the one that it
Because
experiences.
the
Yeah.
flux is increasing that.
Flux is getting bigger in that direction, so it wants to undo that, so it's going to go this way. Okay.
Here we go.
Same deal over here? Same answer? Different answer?
Different answer.
Opposite.
Opposite answer, right?
Yep.
Sweet. All right.
Here's how you do it.
Oh. So same thing is happening, except now we've got the magnet moving the other way. So that means that the flux through this is getting
Smaller.
smaller. It wants more flux going this way.
So it's going to be going
More flux, please.
clockwise.
Right? It always wants to oppose the change. Okay, let's do these. These are the same kind of deals. So this one, just to be clear, this picture is not the best. A north magnetic pole moving toward the coil. So the north pole is moving this way, in toward the coil from above the page. Which way is it going to go?
Yep.
Wait. Go which way are we moving?
From there.
So this way.
Oh, okay.
So the B field is getting bigger or smaller?
Bigger.
Bigger. Bigger into or out of?
Into.
Into. So that means it wants to make some
Out of.
out,
Yep.
out to. So it's going to be counterclockwise?
Yep.
Okay. What about B?
No current.
Why?
Because there's no area for the
There's no area for it to go through.
No area, so no
flux.
flux and no change in flux. Okay. Go ahead and do C and D.
But the velocity of that way.
Okay, so how do we first of all, it's going to be the first one. Nothing will go out.
Your first one's going to be counterclockwise.
Yeah. This one's counterclockwise. And if you point to that
For D, it's shrinking, it's going to have less flux. It's going to
yeah, clockwise.
What do we say for C?
Counterclockwise.
Anti-clockwise.
Counter or anti-clockwise? Do you agree with that?
Yep. Miles says miles.
I watched too much of the BBC. It's an issue.
And how about D?
Clockwise.
Yeah?
Mm-hmm.
One more. I thought, maybe, is it not there? Oh, stink. Where did it go? Oh, no. I had one more that I wanted to share with you.
Some places it's also called.
Hold on, let me find it.
Wait. There's still
Pretty amusing.
Yeah, but it's not there. Yeah, there used to be one more there.